Okay, by now we know a mechanism is a kinematic chain with one link fixed. Okay, but for that fact, can I choose some arbitrary number of kinematic chains and randomly connect the arbitrary number of links and randomly connect those links with some kinematic pairs, and can I call it a mechanism? The answer is in general no, because it should have a relative motion. Okay, it should have a relative motion between link to link, okay, between one link to other. Okay, so that is known as mobility. Okay, and it is also expressed in terms of a variable called degrees of freedom. Okay, so that we will discuss under mobility. And one more thing is important, which is, for example, if I have to have a input or output motion as a complete rotation, okay, in that case, can I have a complete rotation? What is the range of motion of a particular link? Okay, so that is one thing which is important. Okay, and that we will learn under the title range of movement. Okay, so first let's focus on the mobility, which is in terms of a variable called degrees of freedom, which we will denote by f. Okay, so what's degrees of freedom? It's a number which represents the number of independent variables to represent the configuration of the mechanism. Okay, it's a number of independent variables to represent the configuration. So it can be 1, 2 or anything. Okay, so it depends on the application. Okay, so first we need to know how to identify this degrees of freedom for a given mechanism. Okay, so the degrees of freedom depends on two things, at least two things. One is the number of links. Okay, so let's call that number of links as n, and another one is number of pairs, in particular hinges. Okay, so which we shall call j. Okay, sometimes it's been called hinges because we can consider the sliding pair as an limiting case of hinges. Okay, so I'm going to call it just pair. Okay, now let's say if a mechanism is having n links, okay, and the mechanism which we are talking about is a planar mechanism, which means it's restricted to move only in a plane. Okay, so in that case, if we have n links, then it will have 3n degrees of freedom. Okay, because each link can move either in the x direction or in the y direction, or it can have a rotation. Okay, so therefore if we have n links, okay, n unconnected links, okay, then we will have 3n 3n degrees of freedom. Okay, now, and also we have mentioned that for a mechanism we have to have one link fixed. Okay, if we fix one link, we can't have any motion or rotation for that link. So let me take care of that by reducing this n by 1. Okay, so now these many degrees of freedom. Okay, now if I introduce kinematic pairs between the links, what do I get? Let's see. Say there is a link and there's another link, and these two links are hinged together. If they are not hinged together, then say this is link 1 and this is link 2. Okay, let me erase it. That's link 2. Okay, the link 1 will have 3 degrees of freedom and link 2 will have 3 degrees of freedom, but the moment I fixed it, or not fixed it, moment I connect link 1 and 2 using a kinematic pair, a hinged pair, then there will be only 1 degrees of freedom for link 2 with respect to link 1, because with respect to link 1, link 2 cannot have this motion or this motion. Okay, it can only have a rotation, right? It can only have a rotation with respect to that hinged point. Therefore, a hinged point arrests 2 degrees of freedom. So one hinge point arrests 2 degrees of freedom. So it will not let it move in x direction or y direction, but it will let the other link to rotate. Okay, so otherwise there won't be any motion other than rotation. Okay, so each joint will reduce the degree of freedom to 2. So in order to take care, what we are going to do is we are going to subtract 2j, where j represents the number of pairs. Okay, now using this formula we can calculate the degrees of freedom for the planar mechanism. Okay, and this equation 3n minus 1 minus 2j is known as Kurzbach equation. Okay, it is known as Kurzbach equation, and using this equation we can calculate the degrees of freedom. Okay, now let's see some examples. Let's see a well-known example, which is a Phoba mechanism. So this is the fixed link is link 1, this is link 2, this is link 3, and this is link 4. So for this case, n is equal to 4. And what about j? So here it's 1, 2, 3 and 4. Okay, so j is also equal to 4. Now let's use this equation. Let's use this equation. So f is equal to 3 into 4 minus 1 minus 2 into 4, which is equal to 1. Okay, this system or this mechanism is having 1 degree of freedom. Okay, which means if I denote, let's say this is the independent variable theta. Okay, once I define this theta, then I will know the configuration of each link, what is the position and orientation of each link. So that's what the configuration means. So I know the position and orientation of each and every link once I know what's theta. Okay, so just theta is the only independent variable to define the configuration. It has 1 degree of freedom, and using Kurzbach equation we have identified that. Okay, now let's see one more example. So now for this system, n is equal to 5 and j is also equal to 5. For this, f is equal to 3 into 5 minus 1 minus 2 into 5, which is equal to 2. Okay, which means this system is having 2 degrees of freedom. Okay, which means I can't just define the configuration just with this variable theta. Okay, maybe I require one more variable. Okay, maybe some other variable, maybe related to this, another variable theta 2, something like that. So once we define theta 1 and theta 2, then we will be able to define its configuration. Okay, so that's how we use Kurzbach equation and we calculate the degrees of freedom. Okay, now sometimes we will have, okay, but before that I want to introduce a criterion which is known as Groupless Criterion. Okay, so what is Groupless Criterion? It is the Kurzbach equation rewritten for f is equal to 1. Okay, so if f is equal to 1, a mechanism will have a single independent variable, and such mechanisms are also known as constrained mechanism. Okay, and if we see around, most of the mechanisms are constrained mechanisms. Okay, so so for the in the Kurzbach equation, if we substitute f is equal to 1 and rewrite that equation, what we will get is 2j minus 3n plus 4 is equal to 0, and this equation is what known as Groupless criterion. Okay, fine. Now what we are going to discuss is higher order hinges. So what's higher order hinges? Say there is a link, okay, and that has been connected with another link, let's say this manner. Okay, and at the same point, are using the same hinge, a third link has also got connected. Okay, and now let's say this is link 1, this is link 2 and link 3. Okay, now if whether we should count this as connection of one hinge or two hinge. Okay, so now let's say if a body if a kinematic pair connects 3 links, then we are going to count such 3 links as J2, or a small letter maybe J2. Okay, and if in case there's one more link which has been connected, okay, then that particular hinge connected 4 links, then we will call that as, sorry, once again, we'll call that as J3. So in general, if a kinematic pair connects n, or let me use I plus 1 link, then we will call that as Ji. Okay, so if we have such a hinge, okay, if we have such a hinge, then what kind of modification I have to do in the Kurzbach equation, or how should I count this J in the Kurzbach equation? So what we have to do is J should be calculated using the following equation: J1 plus 2 into J2 plus 3 into J3 plus dot 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 I into Ji. Okay, this is how we need to calculate the J value. Okay, once we calculate the J in this manner, then we have to just substitute this J in the Kurzbach equation. Okay, so that's how we take care of higher order hinges. Okay, so such a hinge is known as higher order hinge, and that's how we will take care. Okay, fine. Now what we will do is, how about higher pair? Okay, so how should we account the higher pairs? So if it's a lower pair, we will be able to arrest 2 independent variables, but if it's a higher pair, then we will be able to arrest only 1 independent variable. So therefore what we have to do is, we have to introduce a new parameter h to represent number of higher pairs. Okay, so which means I have to redefine J. So here I have just put number of pairs, but it should be number of lower pairs. Okay, so with that modification, the way I am going to redefine the degrees of freedom f as 3n minus 1 minus 2j minus h, because h is going to reduce only 1 degree of freedom. Okay, so therefore the modified Kurzbach equation is this. Okay, in the next video we will discuss some examples using this Kurzbach equation. Okay, thank you.